Hopefully you're able to hear me. This is Saravanan.
Yeah.
So today we are about to discuss, like we'll start the session because we were waiting till 3:05. So we'll start the session now. So this is about like data engineering, themes data engineering, and then we are going to discuss about like how to optimize and what is Redshift is all about. Okay, so yeah, like if we have to look why and what this Redshift actually is, so it is like data warehouse, a cloud-based data warehouse, and it is being fully managed by AWS. Like we need not have any DBA, so that's the thing that comes along with a cloud-based setup, and like it is optimal for a like OLAP kind of environment where you are having business intelligence applications running on top of your database. Not our current not our conventional like OLTP kind of a system, but it's an OLAP kind of a system. So this like what is the benefit of having a Redshift is like it is going to be faster. Like it is currently proven to be faster than 3 times when we compare with other cloud-based data warehouse that is existing in our current industry. Like it leverages PostgreSQL 8, and then like AWS team has built on top of PostgreSQL, but the Postgres being an OLTP kind of a database, but Redshift has been built like for OLAP. So what they have done is like Postgres conventional OLTP will be a row-based storage. So like in Redshift, it is a columnar storage. So like by switching this context from say row-based to a column-based storage, what we are trying to achieve here is like reduce the number of IO that is happening when we run a query. So that is the main benefit of having Redshift in place. So MPP, like when we speak about MPP, like it is like a massively parallel processing and nothing shared. So this is the architecture, which means like it will have a distributed nodes. Each node will have its own storage, each node will have its own compute, and which will not be shared with the subsequent compute nodes that are present in your Redshift. So that is my MPP architecture. Okay, and then like other default features that are coming along with AWS offerings, that like it is encrypted, it can be encrypted, and it can be isolated from your like in your internet, and then like it is highly fault tolerant. It is also ACID compliant in a way, like it is supporting an eventual consistency, but it's not strongly consistent one. So when we speak about ACID compliance, like then this can be like we can also query our like data lake, which is like in here we will be using S3 as our data lake. We can also query those external tables by using something called a Redshift Spectrum. The name hence like Redshift is started like back in October 12. This primarily started to shift the customer base from Oracle. So that's why this has been named as Redshift. So Oracle by word, like it is having a red logo, right? So we have to shift the one customer at a time from like Oracle environment to Redshift. That's why they have named it as such. So the features that they are using to leverage this is like a MPP and a columnar structure. So that is the key point for this OLAP kind of a database. So that's where like Redshift comes into picture. Wherever we are having any analytical processing that needs to be holding a large amount of data, and it should be faster when compared to a OLTP, that's when we are going to make use of Redshift. Okay. Typical Redshift cluster will have an architecture something similar to here. Okay, so it will have we will have a client endpoint, right? So we will always have a Agility or a SQL Workbench or a Tableau or any dbeaver, any other client that will be your SQL endpoint that will be hitting your query to your leader node. So if we look into a Redshift architecture point of view, we will have a leader node and compute nodes. So compute node can be 1 to 16 or whatever the configuration that you are currently supports. So this is how the architecture looks like. So whenever we are submitting a query, say through your Agility or SQL Workbench, so immediately it hits your leader node. So there will be something called a leader node, which will not be charged actually. So you will have subsequent compute nodes, like compute nodes are where like it will be charged. So if you're having more than one compute node, then your leader node is for free. So you will not be charged basically. Responsibilities of our leader node is something like parse the query, Parsing, by parsing, we mean like we will be constructing a query in your Agility and then submitting the query that will hit our leader node. So the parsing the query will look for the semantics and syntax check. Once that is over, it will build a query tree. So it is going to build a query tree. And then once the query tree is built, then it will generate the query plan and then it will compile the code, pass the compiled code to the compute nodes for further processing. That is the responsibility for our leader node. Okay. And then like when you speak about compute nodes are the ones like where we are going to store the data. Each compute node by itself will have a like say compute, storage, and network connectivity like to support to your leader node. So these are not shared. So shared nothing. So this is not going to share any resources between the compute nodes. So that's why it is like an isolation. Like it's not going to share anything. So shared nothing. So when we speak about compute nodes, like we are in currently third generation of compute nodes. So initial two generations were like DS, DC. So by DS we mean like a dense storage, which is like our good old fashioned like hard disk. So we used to have in our hard disk, right? Like now it has been replaced with SSD. So we used to have hard disk, right? So that is dense storage. So if our requirement is something like we are going to have more of storage and we can compromise on our compute, then we can go for a DS. And then like if our then there is something called dense compute, which is like you will not be getting an equivalent storage, but the compute power will be more in SSD. So that's when we are going to make use of DC. And then like recently we have a newer version coming up called RA3, which is like which makes use of SSD. And then the storage is something like maintained by Redshift managed storage, which we can see in depth about like after a few slides. So for now, like a compute node can be of three types. So DC, DS, and RA3. Okay, the RA3 being the latest one. So where we are decoupling the storage and compute. So that's when RA3 is useful. Like when it is useful, we'll be seeing in subsequent slides. Inside compute node, if we look into, there will become something called slices. A slice is nothing but like a part of, it's like a virtual compute node by itself. It will have a part of storage. It will have a part of compute power that will be that will be processing the data in that slice itself. So if we break down the slice further, there will be something called blocks. Every database will be half of blocks finally. That is where our data is going to reside. A typical OLTP database will have a block size of say 2 KB to 64 KB. Oracle has 64 KB, I guess. And in Redshift, this one is having a block storage of 1 MB. So that is the architecture. Like if we have to look at the architecture at high level, so there is a leader node and there can be more than one compute nodes based on the configuration that we have set. So compute nodes will be further breakdown into something called slices. A slice can be say 2 or 32. The 32 slice per node was available in first generation. When we turn around to subsequent generation, has been like 2 or 16 nodes. And then when we further break down the node, we'll have something called blocks. Blocks is where we store the data finally. Yeah. So what happens like when we submit a query to a Redshift, what really happens? So that's what we are going to see here. So once the leader query gets the query, it will again check for the syntax and check for the semantics. Once these are passed, like once this is validated, it will provide a query tree. So that query tree is sort of an explain plan, like how this query is going to be executed. So that query plan will hit the optimizer. If there is any necessary transformation, say for example, if we run an or condition query, say where employee ID is equal to 100 or employee ID is equal to 200 or employee ID is equal to 300 and so on and so forth, all this will be transformed into an union operation. So instead of running into an or condition, the optimizer will automatically convert this query into separate query and then execute. So it will result in much faster execution. So the optimizer will decide which queries need to be further optimized apart from like whatever query that we are submitting. So once that is over, it will again generate the query tree and it will plan that this planning is going to happen based on the data that is available in your system tables. There are like in every database we have something called system database and system table and system database, system views. Okay, so these are the performance views like which will be aiding us to know more statistical information about the tables that we are querying. So that's where that is called system tables basically. And then like all these operations, once this is completed, this will compile a C++ code. So basically Redshift compiles a C++ code and then submits to your execution engine. So that's what execution engine does. And once the execution engine operation is completed, this will pass it on to the compute nodes. So a leader node operation is like once execution plan is ready, it will compile the code and it will pass it on to the compute nodes. So the compute nodes is the one like which has the data, which has its own compute to process the query that is available inside that node. So that's what it is. Like that's how the query of like life of a query looks inside a Redshift cluster. So if we further break down what is being passed on to a compute node, we will have something called step, we'll have something called segment, we'll have something called stream. So maybe like with an example, we can see what is step and what is segment and stream. Okay, say suppose like we are submitting a table. Okay, so we are submitting a table for like we are submitting two tables. We are submitting a query with two tables being joined. So the first step should be accessing the table. So whatever the table is, whichever the table is smaller, that table will get access first. In here, like segment 0 has a step called scan event table. So that is the first step. And in segment 1, we are having scan internal table project. I mean, like then we are having internal table project and hash this value. So step is first, and then the segment can be multiple steps can be combined into a segment, and then the segments can be grouped together in streams. So since this is not a single compute node, like not all data will be present in a single node. So there are more number of nodes. That's why like we are having a distributed processing, right? So all this processing will happen parallel to each other. Like say stream 0 will be processed here, stream 1 can be processed in separate compute node, stream 3 can be processed in subsequent compute nodes, and so on and so forth. So all these are done parallelly. Like we have steps, segment, and stream. So maybe like we can quickly see how to read and explain plan in Redshift. Before going, so like we are using a sample schema that is taken from Redshift, I mean like demo. So this is the schema that it looks like. So we are having a fact table, sales, and then the remaining are dimension tables. So this is how these are interrelated. Maybe we can come back to the schema if we have any query. So for now, we will take a look into our sales table and an event table. So we are having event ID here, and we are having an event ID here as well. Okay. One more quick reference here is like Redshift does not support any constraints apart from not null. So here we have mentioned a primary key and foreign key, but like these are not going to be enforced inside a Redshift environment. But like if you are providing this, we can have an ER diagram, and the optimizer will understand from this ER diagram, okay, it will have a better planning for it. Say for example, if you are having a list ID column as a primary key in your listing table, but if you can go ahead and insert a null value, you can go ahead and insert a duplicate value in Redshift. That's not going to be tagged as a violation of insert operation in Redshift. But like from other aspect, but this is going to make you, this will be made use as a part of an optimizer while planning. Okay, if it is seeing a list ID as a primary key, it will understand, okay, list ID is a primary key, we can go with this particular approach of solving this query. So we have to bear in mind, like there is no constraint apart from not null in Redshift. So primary key or foreign key that has been mentioned in this diagram are for like only illustrations, and the optimizer will have a better plan for these tables. That's only use case for having a constraint in this. Okay. So this is a sample query. So we are joining our sales and events table. Okay. So this table looks like, so I'm going to have a select event name, sum of price paid, say from sales and event. I'm performing an inner join from the query. We can see this is an inner join. Okay, so this is how our explain plan looks like. So this is how the explain plan looks like. So we will try to read this explain plan right now. Okay, back like when we had a database in 1980s or 1990s, early 90s, we had only something called an optimizer, will be a rule-based optimizer. We never had a term called cost-based optimizer. So this, whatever we are seeing is a cost-based optimizer, because you can see a cost associated to solve this query. Okay, so back in time, like we had only rule-based optimizer. So by rule, what I mean is like we will have a convention while solving this query. So not all, like when I write this query, sales table and events table, we need to know which table should be accessed first. So when we go by rule, the farthest from the flum clause, The farthest from the from clause is event table. So that is the farthest from my from clause. So by this, what I mean is like there are conventions such as inner table or a driving table or driven table or outer table. So here, farthest from the from clause is always an inner table or a driving table. So in this query, if we forget the cost-based optimizer, how to write effectively query when we don't have any optimizers in place. So that's when these things are coming into picture. So farthest from the from clause is event. That is my inner query. I mean like inner table. And like sales is my outer table. So this is the convention that we are following. Like irrespective of whatever we write now to Redshift is always cost-based optimizer. We don't have any rule-based optimizers in place currently. So this is a cost-based optimizer engine. So automatically it selects, say when someone gives a task to one person, like there are two tasks here. One is sales and one is event. So what happens, like which one will be done first? Obviously the one which consumes less amount of power, less amount of consumption of space or storage or compute. So that's the first job that we'll be completing, right? So similarly in here, sales table and event table. So if we look into this plan has to be read in a top to bottom fashion with the most intended one being the first being executed. So read it top to bottom, but the most intended one being the first to be executed, okay, to be accessed, okay. So if we look into this query plan, the most intended one being the sequential scan on event table, okay. This is a step. Whatever is indicated by an arrow is a step. So this is a step. So this is a step. So here, this is a step. Every arrow is a step. Every arrow marked is a step. Okay. So this is like a tree, like a structure. This is a query tree, like a structure. So this is having a cost, rows and width. So, okay, we are having a cost of 0.00 and double dot 87.98. Okay, these are two decimal values, 0 and 87.98. Okay, the first cost, like this cost is 1. This is an unitless value. It does not have any unit like a second or a hour, or it's not saying bytes to be processed, or it's not saying percentage used, nothing. This is a plain number, a relative number, which doesn't have any unit to it. Okay, so when I say xn sequential scan on event table, so what it does is basically the first value 0.00, this first value, you can see first value 87.9800 and 109.98, and then we are having a bigger value here. So the first value across this plan indicates to retrieve one row from this query, what is the effort that I am going to take. So to retrieve one row from the scan, like from the event table, it is going to be 0.00. Okay, as I traverse up to solve this entire query and return one row, this is the cost for returning one row. The next cost that we are seeing here, 87.98, is say sequence, like event table is having 8798 rows. In order to return 8798 rows, I have to put an effort of 87.98. So that is the value. So it's a computed value which says in order to access all the rows from the event table, my overall cost will be 87.98. So this is the cost. So cost will be two values. First value represents, like, to return first row, what is my cost? To return all the rows from event table, what will be my cost? So that is what this cost is. It is an unitless value. So we have to take that in mind. It is an unitless value. It does not have any unit like a seconds or hours or milliseconds or nanoseconds or percentage, nothing. It's just a pure number. It considers a factor like how you see, like same query, same, like we are running the same query in two different sessions, we might end up with having two different costs, because cost is purely depends on your tables, your cluster, like your cluster, your CPU utilization of your cluster. So these are two major factors that are going to be considered while giving an explain plan. Okay, this is the explain plan. This explain plan is not going to run the query. Okay, say for instance, like if you're asking for me to move from Adyar to Tiruvanmiyur, I might have 10 possible routes. All the 10 possible routes will be considered by Redshift optimizer. It will pick the ideal route which is fastest. So that's what it does. And it gives an indicator like, okay, first row to return, this is the cost. And to complete the operation, this is my cost. And I'm expecting this many rows to be coming. Width is something like 21. If it is saying 21, it is saying like 21 bytes long. So whatever the rows are that are going to be returned from this step is going to be 21 bytes long. So that's what it means. Hopefully this far it is clear. We can traverse up and then we can complete with explain plan, and then we can move into demo. Okay. So this is first, whatever is happening here is a sequential scan on event table. Why event table we can see? So there are two sequential scans here. One is sequential scan on sales, one is sequential scan on event. But I'm saying like event table is going to be taken first. Why? Because 8798 rows are present. In here 172456 rows are present. Like by convention, the one which takes least amount of compute, least amount of resources to be spent to solve an operation will be taken first. So in here, the event table being a dimension table that is having less number of rows, 8798 when compared to our fact table. So that's when like we are going to have event table first. This event table will be completed, like this event table operations will be completed first. And then like once this scan is completed, it will develop a hash value for all the rows that has been retrieved from this event table. So once the event table is done, like what it is going to do is like it is going to access the sale table. So from when I execute this query, first thing to execute is event table. Once the event table is hashed out, and then it will move on to sales, it will generate a hash and then join these two hash values. So that's what it is. So once this is over event and then hash is over, it goes on to sales, it provides hash value, and then it joins these two by using something called a hash join. We will we will go deeper into these terminologies. All these are called as operators. So a sequential scan is an operator. DB, a broadcast inner is an operator. Hash join is an operator. Hash aggregate is an operator. All these are operators. So by the time I run this query, I am going to expect 581 rows to come out of this query as an output. So this is my expected rows. Okay, so 581. I'm expecting 581 rows from this query to come out of this. Like by the time when we complete this query, it should be 581 rows. That's what this explain plan says. And this is going to be the cost. Okay, the remaining things we will be discovering later, maybe a couple of slides later. Okay, for now, understand like an explain plan will have cost, rows, and width. The first cost is like to retrieve first row, what is the cost, and to complete the entire operation, what is the cost here. And rows, this is speculative amount of rows. So say, for example, you are moving from Madhya to Thiruvanmiyur, you will have 10 different routes, right? So you will have an understanding, like if I traverse to route 1, I will have no signals. If I traverse to route 2, I will have 10 signals. If I traverse to route 3, then I will have road condition being very sloppy. Okay, these are statistical information that we collect as a part of cost-based optimizer. So this is stats information. If your statistics is stale, then your explain plan is going to be like looking odd, like it will not be optimal. So suboptimal explain plan will result. So these are operators. You will see cost, rows, and width. So this is a quick walkthrough on explain plan. Okay, and then we will move into something like what are the operators or join algorithms that are widely used or that are frequently seen in an explain plan. That's what we are going to see now. As I mentioned, like more often than not in Redshift, we will have something called sequential scan on some tables coming up. Okay, so we will have something on sequential scan. So this is being the least one. So whenever we are seeing an explain plan, you will always see a sequential scan on some table. So it can be an event table, it can be a sales table before even accessing to that. So an operator that is like a sequential scan on operator, which means like that means you are going to scan the entire table. Whatever is filtered out from where clause, those things will be scanned. Okay, and like we are having two tables, right? So we are having sales and events table being joined here. So whenever we join, there is an algorithm that steps into how to join these two tables. So that is called as a join algorithm or join methods, or we can call it as a join operator in Redshift terms. Okay, so how we design our table influences what join method that I'm going to use to join these two tables. So those are three types basically. We are having a nested loop, we are having a hash join, and we are having sort merge join. In here it is called as a merge join. Okay, so a nested loop is an ideal use case, like say you are having a for loop within a for loop, like you are running two for loops nested within one another. So what happens is like we are having an outer for loop and we are having an inner for loop. For every value in outer for loop, inner for loop will run that many times, like whatever is there, it will run one time. So second, it will run one time. Third, it will run one time. So this is a use case like a cross join, right? So this is a cross join. So in OLAP, this is the least optimal join that we can find while joining two tables. So if you are finding in your explain plan a nested loop, then you have to investigate deeper into the query why this is happening. So whether are we missing any join conditions that we have to investigate. So make sure, like if we are using in a OLTP, that is a different use case. In OLTP, like we will have a index, right? So in OLTP, we'll have something called index, which is not present here. So a nested loop in OLTP could be a better one, But a nested loop in a OLAP environment where we don't have any index concept, that means like whether we are missing a join condition or it's going for a like cross join. That's what it is. So we should not be seeing any nested loop unless until it is a cross join. If we see, then we have to investigate the query. That's it. That's it with the nested loop. A hash join. So there are three basically. So hash join is the second best use case of join algorithm. Okay, so hash join is like going to take an inner table. There are two tables in any join. So we are going to have an inner table. We are going to have an outer table. Inner table by convention, it should be small in size. I mean, like outer table can be a large one. Okay, so inner table will be hashed and then outer table will be hashed. It will be joined together and then it will be providing result to the client. So that's how hash join works. So it is going to hash and then join. So that's why it is known as hash join. Like when this will happen in our Redshift environment is, say we are like our tables are going to be sorted and stored. So when we consider like how to store the data in our Redshift, we will have a better understanding why when we can go for a hash join. Okay, so for now, like understand the smaller table will be hashed first and then the bigger table will be hashed next, and then these two will be joined based on the hash value. So when this will be used, we'll be discussing in subsequent slides. Okay, so sort merge join. Exact keyword for this join is a sort merge join, but in Redshift we call it as a merge join. Why? Because like all our data in Redshift can be sorted and loaded. Okay, so that's why the keyword of sort is not mentioned here. Like this is going to be the fastest join that we can achieve in a OLAP setup. Okay, so if we see a merge join, that means like almost like all our queries are running fine. Hash join is also fine. A nested loop join algorithm is not recommended to be seen in your OLAP setup. Okay, so merge join, when it is going to happen is like we are having a provision to sort the data and store it in our Redshift. But say if your table is say less than 20% of the tables is unsorted, out of 100, if you're having only 20% of your rows are not sorted properly, then this will automatically fall into merge join. So this is when it is going to go for a merge join. But a hash join is something like if it is more than 20%, the second best join is hash join. So it will go for a hash join. So more frequently we'll be finding hash joins in our explain plan. Nested loop should not be found. Merge join, like yeah, we can find it on and off. Like if our table is so good, if everything is so like if everything is aligned properly, then we often see merge join in our explain plan. Okay. Okay. So we are having sequential scan operator, join operators, which can be classified as nested loop, hash join, and sort merge join. And then there are other operators because we are having different compute nodes, and there will be network related and back and forth network related operators will be there. Those are disregarded for this discussion, but we are going to aggregate our results, right? So I'm writing say select query, select sum of sales from sales. That's what I'm going to write. If that is the query, then you can find a keyword called aggregate. So that is a scalar aggregate functions. Just a plain select with sum of or average of or min of or max of, that will result in seeing an aggregate. And then hash aggregate is something like you are going to select a column, say select say department ID comma sum of salary from employees table. So your department ID is not sorted, and then you are going to find hash aggregate. If you are going to find say select say job ID comma salary sum of salary from employees table group by say job ID, and provided your job ID is sorted and stored, then it will be falling under group aggregate. So these are frequently found explain plan operators that we will be finding in our day-to-day activity. Like so far, if there is any questions. So okay, we will proceed to the next slide. Okay. Okay, in here, like this is not a OLTP kind of a setup. So this is OLAP, and then we are having column-based storage. So there is something called how to best design our table. So how can we design a table so that the design part of the table is being taken care of? The first thing that we have to consider is something called distribution. So how do we distribute data? Because like since all the nodes will not have all the data, so we are having something called distributed nodes, distributed compute nodes, right? So we'll have 1, 2, 3, and say 10 nodes will be there. So all 10 nodes will have equal amount of data or same amount of data, or else like all data will be available in all nodes. So that is something called as a design consideration from a data distribution point of view. So we are having multiple compute nodes, and then we have to distribute the data amongst these compute nodes. That's what the design goal is all about. So we are having three different distribution style. One is key. Say for example, we can take a column. That column, say if we are saying like I'm running a company, I'm having a department ID column, and under each department I'm having only 5 employees. Okay, we are having 10 departments, so we can expect 5 employees out of each department. So that is an uniform distribution across whatever we are having, right? So in such cases, if any key column, say here I'm mentioning a department ID, in each department ID I'm finding 5 people working, so that is an uniform distribution. Whenever I'm able to find a close to an uniform distribution kind of a field, then we can go for a dist style based on a key. So there are dist style, so that is key, all, and even. So when we can go for a key is whenever we are having a key value, whenever we are having a column that lends itself for a uniform distribution or near uniform distribution, that's when we have to go for a key. So by doing this, so we are having node 1 and node 2 and node 3 and node 4. Nodes are divided into slices and then blocks. So every time when I'm saying 10, 10 will fall under this bucket, 20 will fall under this bucket, 30 will fall under this bucket, 40 will fall under this bucket. So 10 5 times will be here, 25 times will be here, 35 times will be here, 45 times will be here, because we are having 5 employees in each department. So if it is lending itself for an uniform distribution, then we can go ahead with key-based distribution style. Okay, we have another distribution style, something called all. So this all indicates something like, say my table is relatively less. I'm having only 500k rows to 1 million rows. Okay, my table is relatively small in columns as well. Like I have only 5 columns. So that is a small table in Redshift standards. Okay, so if that is the case, what we can do is we can populate our small table across multiple compute nodes. So I have only say 500 rows in my departments table. I can have my departments table in node 1 entirely. I can have my departments table in node 2 entirely, node 3 entirely, node 4 entirely, node 5 entirely, and so on and so forth. How many nodes, whatever we are having, we can populate my data across all nodes. Full copy, like full copy of my departments table will be present here. It will be present here. It will be present here. So always like it will make use of the first slice. So once the first slice is filled, then it will go for the subsequent slice in your current compute node. So this is all, and all cannot be used for a larger tables like a fact table, because like if we are going to use a fact table, it's going to be huge in size. We have to maintain the same copy in every compute node. That will be like a storage intensive task, and then we are going to be charged for it. So all should not be used for a very large table. It can be ideal for a small dimension tables. Okay, and then even, okay, so in first example I said something like an department ID, right? So department ID 10, and then I have 10, 20, 30 each being having a 5 value. If that is not lending itself, like I have an employee ID column in my employees table, which is going to be unique, right? So we don't have any department ID column. So we don't find any particular combination that lends itself for a uniform distribution. Then we can go for something like an even distribution. Without having any distribution, like we can go for an even distribution. So this is about how to distribute the data in various compute nodes across my Redshift cluster. Okay, so okay, now like we are having something called redistribution. Again, we are going to continue with our explain plan here. So as I said, like we can distribute based on a key, we can distribute entire table, or else we don't have any key to lend, or else we cannot go for an all distribution, then we will go for an even distribution. So if we are, not all tables will be falling under key, not all tables will be falling under all. So it's going to be a mixture of all these three. Okay. So when we have these things in place, and then we will have a necessary to join multiple tables in a query. So that is when we are going to have some concept called redistribution of data. So redistribution can happen in 2 ways. Like that is going to be a broadcast. A broadcast is nothing but sit here and broadcast to every other node. Say I'm node 1, I will have some data with me, and I will pass on my data to every other compute nodes. So I have one. I will be broadcasting my messages to all other compute nodes. That is one style of doing things. The next style of doing things is redistribution. Okay, I don't have to speak with all other compute nodes, but I have a value which is required in node 3, and then I will speak with node 3. I will transfer my data to node 3. So that is redistribution. Okay, so why we do this? Because like in order to have an optimal plan, so I have a 10 cluster. My cluster size is 10. I have 10 compute nodes. So all 10 compute nodes should have an equivalent compute, like that's like equivalent, what to say, like equivalent workload that should be allocated across the 10 compute nodes. Say if node and if your node 2 is free, and if your node 3 is free and node 4 is suddenly getting busy, then that will be like a suboptimal storage plan. Okay, so whenever we are distributing data, you have to keep in mind like all compute nodes should have an equal weightage, equal workload. That's it, that is mandatory. That is when we are going to consider redistribution. Okay, so this is point one. And as I said, like if you are going for a key based distribution, one more point is like a key column, if it is having so many null values, kindly avoid that value because your data is going to be skewed. So that's one point. This is again like we covered before, like inner table, what is an outer table? A smaller table is called an inner table in a query. A larger table will be an outer query. Okay, outer table. Okay, so inner table will be kept in memory, processed in memory, and then outer query will be read from the memory. I mean, like read from the disk. So that is for inner and outer table difference. So when we speak about operators, right, we spoke about operators a couple of slides before. Those are like sequential scan, nested loop, hash join, sort merge, hash aggregate. We are going to continue with other operators that we are going to see more often. Okay, so those are these. So these are the operators that are available. These are the keywords that we have to hunt for in our explain plan. Okay, so maybe I can, like, without even walking through, like I can quickly point out which is ideal, which is the best use case, and which will be the worst use case. So these two, right? So dist style all none, dist style, I mean like ds dist none. So these two are, if these two are present in your explain plan, we are very good actually. So what it means is like dist style, ds dist none means like I don't have to locate, like I'm joining two tables. I don't have to, like don't have to pass on my data to other compute nodes, to our other slices. All our data that I'm trying to join is within me. So I can join within myself and then provide the data to our leader node. So that is very easy to do. Okay, I don't have to pass on the information to other nodes and look for the information correspondingly. So that back and forth will not happen in here. Okay, and I said like we are having another data distribution style called all, right? So what all indicates is like I have a smaller table. I'm going to keep a copy of entire table in all my compute nodes. So if you are seeing this one, which means like my inner table, like, okay, inner table, whatever smaller table, right? So that is called inner table, that is distributed across all the nodes, so that I don't have to distribute the data outside my node. So that is the second best case that we can find. Okay, these two are the best cases. The third best case, if we have to point, like this might be the one. So like ds distribute inner. So my inner table is having a part of information which might be helpful for computing in the node 3. I'm node 1, node 3 is having part of my information in some other table. That's when I'm going to distribute my record from my inner table to the outer table. So that is when this is going to come into picture. And then, okay, so this is another use case. So ds bcast inner. We saw a couple of slides before in an explain plan, this keyword was present. We will walk through what is happening here. So ds bcast inner, which means like my inner table is also key based up, like it is also segmented key based. So it is segmented key based, but I'm joining to a fact table. What happens is like my inner table will broadcast the entire streams of data to all other compute nodes. So this is the next worst case, next best case that we can consider. And then like ds distribute both. Okay, what is happening here is I don't have any distribution style that has been picked. So we have all, we have even, we have even. For example, we don't have any key column, or we don't have all applied in our table. We have something by default called even, right? So that even when we are having two tables without any proper distribution, then we will find all the tables being distributed across all the nodes. So this is the point like where your CPU utilization will go to peak. Okay, because you're distributing entire data to entire nodes. Okay, and then like if you're distributing your outer table, that is a bad design. So your outer table by convention, it will be a larger one when compared to the inner table. So if your outer table is going to be distributed across, it's going to be a nightmare for your Redshift cluster. Okay, so this is next worst case. And ds distribution all inner. Okay, sorry. So what happens here is like the inner, like by convention we said, right? So an inner table can use an all configuration, like a dist style all. But for some reason, if someone is designing a table, a fact table perhaps with an all style, so my entire fact table will sit in the node 1 slice 1, node 1 slice 1. But my inner table, that has to be right, that has to be the smaller one, is distributed across all the nodes. Then what will happen is like entire table should be distributed, because the outer table, that is a fact table, is using dist style all. This is a suboptimal distribution technique. So more often than not, we have to find this in our explain plan. That is when we are going to have a good query execution runtime or compute power. So that's when we are going to use optimal storage or optimal compute or like optimal time to get a query to the output stage. So this is with redistribution. Okay, maybe we have to go back in time. Okay, so in here you can see something like a DS bcast inner. Okay, so as I said here, we are having two tables, sales and event. Here event table is inner because event table is smaller in size. Okay, so what it is saying is DS bcast inner. Sales is also like sales is what to say, like we will look back into the DML. So we are looking into two tables, like one is event table and another is going to be our sales table. Okay, so event table and sales table. So in event table, I have event ID. In event table, I have event ID as short key in this table, right? So whatever I have created, this is having event ID as short key and event ID as dist key. Sales is going to have some other ID. Okay, both tables are having dist key mentioned. Both tables is going to have dist key that is going to be mentioned in our database. Like once again, maybe I can show a demo. Okay, so you can see my event table is smaller table, but it is having a dist key style of distribution, and it is using event ID to distribute across the data. And we can quickly see in sales table, we are using list ID. So we can see in our sales table, we are using list ID. So this join is saying I am going for a DS bcast inner. Why DS bcast inner? Why? Because like this event ID is not present. This event ID is not distributed in sales, but in events table, event ID is distributed. Okay. So what is happening is my smaller table will broadcast entire rows that is present in each compute node to every other compute node. Okay. So that is what happening here. Okay. As I said, like event table being a smaller table in this example. So as we said like a couple of slides ago, yeah. Event table is a smaller size because it is having only 8798 rows. So what we can do is like instead of having a distribution style of a key based, we can go for an all distribution style. So just keep a track of this number. So how large the number is, like this is a relative number, 281 and some more digits and 70. That's what we are having as a cost to execute this query. A few steps later, what I'm going to do is like I'm going to change the distribution of the event table. So distribution key all and even, right? So what I'm going to do is here in this query, same query I'm running sales, and I'm just creating another table, event all. Maybe I can show a demo. Okay, this is the cost for the same query that we have in PPT. Now I'm going to slightly modify this query. Okay, so I'm going to drop this table called event all. I'm going to so event table I'm going to, I mean like I have an event table already. I'm going to create an event all table with the dist style all. So instead of having a key based style, I'm going to use dist style all, and we can see the query how it performs. Both are same query except the table. So the table is created now, and I'm going to run the query. We will compare this cost, overall cost, what is happening, what is the explain plan that we are seeing here. Okay, you can see DS dist all none. What happens here is like event table is already available in all compute nodes. I have 4 to 5 compute nodes. If for example, say 6 compute nodes, in all 6 compute nodes, I will have the 8798 records being placed. But whereas my sales is distributed by some list ID column. Okay, that's when like you are going to see DS dist all none. So this is an optimal plan. So we had a cost to compare, right? So we had a cost to compare, like what is the effort that it takes to execute this query. So you can see the same query I'm running here. event sum of price paid said, and I'm using a new table that has been created in place of event. So you can see the overall cost from 28 and some numbers.70 has been reduced to 8389.70. So which means like the query that I have now in hand is going to be executing much more faster with much relevant compute requirement with like more ease, like when we compare with this query. So this is a suboptimal query strategy. That is a suboptimal storage plan, but an optimal storage plan will look something like this. So optimal storage plan will have a cost being reduced to something like this. Why this cost is getting reduced? Because you are finding a join operator, ds dist all none. But here you are seeing my smaller table has a necessary to broadcast every record from one node to all other nodes. So that is why it is having this much cost, and I don't have any need to broadcast anything. So that's why the cost is reduced here. So this is how explain plan works. So this is how a table should be designed basically. Before we move on, we have to review further, like we can review further explain plan as a part of this activity. Okay, here we are having sales, listing, and events. So sales is having list ID, listing is having list ID. Hopefully you are able to see my screen. So sales is using distribution key as list ID, and I have a listing table. It is also using list ID. Okay, so whenever we have a need, so we will go back here. Yeah, so this is what we saw now. Whenever we have our list ID being like what to say, like list ID is a distribution key in my sales table, list ID is my distribution key like listing table. So whenever we have this setup, so when I'm joining listing with sales, it will always go for ds dist none. So there is no requirement for any broadcasting or any distribution, because all my join key columns can be coexisted within the same slice of the same node, so that we will be the query execution will be much more faster. So you can see how it is joining. Okay, so this will be a relatively complicated explain plan. Okay, what is happening here is when I'm trying to join my sales and listing table, you can see here sequential scan on sales, sequential scan on listing. These two tables are joined by a join operator called ds dist none, because I don't have any necessity to distribute any record from any of the slices to any other compute nodes or the same compute node. All are co-located, which means like list ID, say list ID from sales 10 can be say list ID from listing 10 will be present in same slice of the same node. So I don't have to traverse back and forth. That effort is reduced here. That's why it is saying ds dist none. Okay. So these two are joining using a optimal join plan, and then we are having an event ID field, right? So event ID field is something like you can see here. Event ID field is like event table, right? So event table is having DB broadcast inner. Why? Because my event table is having an event ID as my dist key. That's why you are having a necessity to broadcast my event table to all other compute nodes. But maybe we can tweak this by using another table called event all, then give an alias name event, and the query we can check now what is happening. Okay, so now you can see this is the best query that, I mean, like this is the best that this query can be executed on. So you can see both ds dist none and ds dist all none. So basically sales and listing doesn't have any distribution job to taken care of, and event table is also having an all distribution. So I don't have any requirement to broadcast anything to any other node. So relatively the cost will be less for this query when we compare with the previous query. So this is how a table design should be considered into factor, like before even proceeding for some like how to design a table, right? So this is a designing phase of your table. So these are the factors that we have to consider. So like we have close to 7 tables in this schema. We have constructed a query that will have all 7 tables in this query. Like all 7 tables in this query, we are having all 7 tables. Say for example, we are having category, event, venue, sales, listing, date, and users. All 7 tables are present. We will quickly just see the explain plan for this one. Yeah, this explain plan is going to be pretty large. So whatever we are going to see here is like we can just observe how this is getting joined. What is the operator that we are using? So it is broadcasting one table, again another table, another table, and only listing and my other table is going to be coexistent. So listing and sales tables are going to be coexistent. The remaining tables, everything is going to have a broadcast operator. So it is going to be broadcasting how many tables? Close to 6 tables I have to broadcast because of my table design being inefficient. So let us observe this value. So let us have this, let us open a new tab. like what I'm going to do is like all these tables, right? So whatever tables that I'm showing here, all the dimension tables are based out of a dist key method. Like we are using a nick key. In event table, we are using event ID. Venue table, we are using venue ID. In sales table, we are using list ID, right? And so on and so forth as a dist key. What we are planning to do is like we are going to create another table, another set of table in another schema. So that is this schema. In here, I'm going to have a DDL, right? Having a DDL, I have a dist style all for dimension table. My user table will be present across all nodes. So my venue table will be present across all node. My date table will be present across all node. Event will also be present across all node. Listing being a like huge dimension table. This is a dimension table. So this is a dimension table, but we are going for a dist key method. So list ID, because list ID is joining directly with my sales table. So these two tables are huge in size. What we are trying to achieve is minimize the compute, minimize the IO. That's what our key goal is here. So we are having list ID and we are having list ID. So we are going to join these two as a join field for this structure. So we are going to have dist key as list ID. Here also dist key as list ID. Remember, like we have only one field has a dist key. For sort key, we can have more than one field. So maybe like all the tables are dropped. Quickly, I will run the DDL statements and then I will insert the data from other schema. So I'm currently having the data schema. I'm going to I'm creating all these tables now. I'm going to copy all these tables data from public schema. So I'm going to transfer all this data and I'm going to gather stats. So this is our like Redshift way of gathering statistics. That stats is going to be like gathering statistics about the table, how many null values are there in each column, how many distinct values are there in each column, how many rows are present in each table. So that is something that is analyst going to do. So that is gathering stats as we execute this query. So now analyze command is running. So once this is over, we will have the same query rewritten. So same query whichever we saw here, right? So we saw this query, right? So I'm rewriting the same query, but with a different schema. Instead of public schema, I'm having a data in this schema. So I'm going to run this query and I'm going to see the cost. I'm going to compare with the final cost of this one. Okay, and I'm going to evaluate what is the like broadcast mechanism that has been used. So here we are seeing 1, 2, 3, 4, 5 tables out of 7 is going to be broadcasted. So that is like intensive task for any Redshift cluster to be handling. So instead of doing so, like I have used a dist style all. So let us evaluate the cost and what is the distribution mechanism that it takes. Okay, so if we go up here, yeah. So if we see this 1, 2, 3, 4, 5, all these 5 tables, instead of having a broadcast, now it is having dist all none. So the effect of this can be seen in the cost, the final cost, right? So we have to see the final cost. I have this. So this is a new table. So new table, old table, I will copy the final cost. So the cost is something a cumulative value. So as we traverse up, like from bottom up, the final value will be here. So this is a cumulative value. So this is the final value that we have to take care of. Okay. So this is the new, this is the old table. So old table by design, it is having, this is the cost of old table. Old. And this is the cost for new table. So you can see the cost is also reduced and the distribution mechanism also reduced. So whenever we more often than not, like we will be having a scenario where we have to join 10 tables or 11 tables or 13 tables or like say 10, like 5 tables, it can be any number of tables, but like we have to ideally plan for how we are going to distribute the data. So that's where we are going to optimize the query, say to 80%. Okay, so we can clearly see the benefit of having a proper design to our table. So the new one is having a far less value when we compare with the old one. So that is what we are achieving by using a proper distribution style. Okay. So quickly, yeah. Yes,
Yeah, hi, this is Sriram here. Just a quick question on here.
Yep.
Let's consider the solution that you have explained. That works if it is if it is the tables are in smaller in size, right? If it is the data are
Yeah,
stored in each and every instance, correct?
correct.
So what if it is a half to half? Let's say five to seven tables and 3 to 4 tables are very huge, and some another 2 to 3 tables are a little smaller.
Yeah.
Is there any chance to optimize that, or it has to go through the process cost?
Okay, this is like an iterative process. Like we need to have a better understanding of the volume of data that we are going to deal with. You can see a listing is also a dimension table basically, but a listing is joining to sales table by using list ID. Instead of having list being like propagated into my all of the nodes, I choose to have a list key called list ID. Because I'm going to have sales is my fact table, which is close to 200,000 rows. So it will be easy for me to have this to be distributed on the list ID field, because both these tables are going to have list ID in the list key. So say a value of 10 can be 10 and 10 will be coexisted in same slice of same node. 20 will be same slice of same node. So that is something that we have to consider the size of data that we are dealing with. Not everything, like we cannot completely ignore this DS bcast inner. There will be instances like where we have to have all these operators coming into picture, but we have to design in such a way like how we can reduce, like is there any way to reduce seeing the DS broadcast inner, and if you are seeing DS broadcast outer, so is there any way that we can distribution can be reduced? So that's what we are trying to achieve here, that like can we have a better idea of how the records are going to be joined, and like overall data volume, that is statistics.
Yeah, I got it. I got a good understanding. Like, my question is like, let's say, if we go with the starting joining small tables, then going with the bigger tables will give benefit, or joining big tables first and then going through the small tables is efficient. Is there any
Yeah,
on
like
that?
that decision, right? Like whatever we are saying, right? Whatever you are saying, like that is something like rule-based optimizer. But
Yeah,
currently we don't have,
almost like yeah.
yeah, we don't have the privilege of selecting whether we are going to work on a rule-based optimizer or a cost-based optimizer. Oracle still does have something like a rule-based. I can switch it to a rule-based optimizer. Like that is when like we are going to have the outermost table from the from class should be the smallest table. Okay,
Yeah.
the one that is going to be close to the from class should be my fact table.
Okay. But
Okay,
here we
so
cannot choose that kind of scenario. Is that?
yeah, we don't have any privilege because like they
Okay.
are using machine learning to have this query optimized. So which is like they believe like it is going to be far more updated in terms of statistical information about the table than we are. So that's why they have disabled. I was about to explain a few things about like something called hints. So in like this is something called hints. Okay, we are having hints in Oracle, we are having hints in MySQL, I guess, and then we are having something in Postgres as well. But that feature of, say, for example, these two tables, event and venue, I'm forcing. So slash star plus and then writing a keyword, and I'm using two table alias name, and then I'm closing the comment. So this is called a hint. So in I say if I'm using this in Oracle, so what it will do is like say event comma venue will be joined by using a merge join, sort merge join, rather than going for a nested loop or a hash join. So say your query optimizer chooses a hash join, but I can force it to use a merge join. That privilege is not available in Redshift.
Okay. Yeah, got it. So,
Okay, so like by designing a proper, like how to design a table properly, then we can achieve or we can minimize seeing these operators. Like most of like suboptimal things are like you cannot broadcast your outer table, that is not going to be good. You cannot broadcast your both the tables, that is again not good. And you can never have your like a fact table being present in all your nodes. So this should be avoided also. So if you are finding like we cannot ignore like broadcast in a table, that cannot be done, that cannot be completely eradicated. That's why we are having it here in this table. But there are instances like where we can reduce, where we can tweak the table properties so that we can execute our query in a proper fashion. Over to Durga.
Now we are going to see a concept called as a sort key. The sort key defines how the table data has to be physically stored in the disk. This is done by a concept called as zone maps. Zone maps, basically what it does is, in a block, whatever data has been stored, it will store the in-memory block metadata, which is a min and maximum value of what is being stored in the block. So whenever we have to give a particular var condition, the columns that are being used in the var condition frequently will be used as a sort key. So whenever a value has been chosen, the value will be checked with that of the zone maps and decide whether the block has to be scanned or not. So the pooling of data will be effective when we choose the correct sort keys. Sort key can be chosen on, there are two types of sort keys. One is a compound sort key and another is an interleave sort key. Both defines how the data is being stored in the physically how the data is being stored. When we go into the compound sort key, can you go to the next slide, sir? When you go to the compound sort key, when you select two or more, you can select two or more sort keys. When you can select two sort keys, it will define the first column. Whatever column you choose as a first will be used to sort the data first. As in this case, let's just say the customer ID will be choose to choose the data which has to be stored in the block. In the customer ID 1, we can see that entire data, depending on the customer ID 1, it is stored on a single block. And for 2, 3, the customer ID, based on the customer ID, the block has been selected. So if I had to query customer ID 1 in the first case, I will see that only one block has been accessed for that. But when I select a country ID 103, 4 block items will be accessed. But in the second case, which is an interleave sort key, let us say the first, the compound sort key will be chosen when you know that a particular column could be used most frequently for a particular table. Let's just say I have a fact data in which I have a date column. More or less, whenever a BA user hits a query, they will usually filter based on the date condition. As in, they will be interested only in a particular date column, a date range, and hence only that date range will be filtered. So the input-output operations will be reduced. So in that case, the first thing will be preferred, but there will be tables in which two columns will be most frequently used in the var clause. Like just say customer ID and item ID. So the interleave sort key was as in it will be stored based on the two columns. The two column values will be chosen to select which block will be used for the storage. So in the second case, if I have to select a customer ID 1, I will be accessing 2 blocks of data. Whereas in country ID also, if I have to select 1 or 3, here also 2 blocks of data will be accessed. So it will be a trade-off between 2 columns. We can go for an interleave sort key. But interleave sort key, when you don't prefer an interleave sort key, is when you are choosing a column which is monotonically increasing. Just say a date column, because as the data increased, it will become more complex and we use the interleave sort key. Next slide. Now we will see what is the compression. As we have mentioned before, Redshift is the column-based storage, and compression also, it allows you to mention compression for a particular column. So based on your column type, you can specify which compression format will be used. The compression will compress the data and store it in a block so that the storage space can be conserved, and the input-output read operations from the disk to the memory can also be reduced. The important key consideration that you have to consider here is whatever column you use it as a sort key, you don't usually compress it. It is not best practice to compress it, because if we compress it, the particular the many sort keys will be stored in a particular block, because of which many rows can be stored in a particular block, and hence the read operation will be more expensive. So mostly sort keys will be given a raw data compression format, and also AZ64 is a new compression format which has been introduced now, which is optimal mostly for date formats and also for numeric formats. And for var and varchar, the Redshift automatically assigns a LZ compression. The compression format we will see later. Can you go for the next slide? Okay. Workload management. Workload management defines how you can manage your load on your cluster. So workload management basically allows you to create query queues based on the utilization. Let's just say we can, based on your workload, you can define user groups. Let's just say there will be BI users and also ETL users and also ad hoc users to your cluster. The BI users could be given more priority because their reports is of higher priority. So when you have to prioritize one set of queries over another, we will go for a WLM settings, in which, let's just say for a BA user should be given more priorities. We can set 2 kinds of metrics, which is one is concurrency level, another is a percentage to use. Concurrency level will specify in a particular queue how many concurrent queries can run at a particular time. And also memory percentage to use will define how many percentage of memory the queue can access the cluster on. So you can specify these two and also user group. Let's just say for our use case, we will create 3 user groups. The VA users will be more prioritized. So a number of queries of VA users can run concurrency can be set from any number from 0 to 50. And just say ETL. ETL are most extensive jobs. So let's just say a number of ETL jobs has been running on a cluster. The cluster utilization could go really high. So we can restrict the number of users at a memory percentage that a ETL user can submit on it. So these kind of restrictions can be given on that. So based on this, let's just say I submit a query. The query doesn't come under any of the query groups that we have mentioned. Then the query will go to the queue. It will wait for a queue to become empty before it submits it. So the waiting time will be increasing. So we have to we can use the workload management efficiently to enable which priority results are obtained faster. And also we have 2 default queues. One is a short query accelerator, which we can enable or not. Short query accelerator, basically what it does is, let's just say an extensive job has been running on a cluster. For that, my small jobs have been waiting. In that case, when we enable the short query accelerator, it will see it will have a dedicated queue for the short queries, and we can define the short query based on the number of and the time taken for the query. Let's just say we can set any number from 1 to 20 seconds. So the short queries will be submitted on the dedicated space, and the short queries doesn't have to wait for a long running query. Can you go to the next slide? Now we will see the different table maintenance operations that we maintain to maintain our table. The first one is analyze. As seen before, whenever you create a table, the table statistics will be very updated. So your query plan will be most optimal. But as we insert or delete data or update your data on your table, your statistics will become stale, and hence your query plan will be less efficient. So what we can do is we can run an analyze command, which will update the statistics of your query. The analyze command, it is kind of an extensive operation, which you needn't have to run it on your entire table. We can run it on specific columns. The most specific columns that is advised to be run on analyze is sorting, whatever columns have been using in sortings, joins, and where conditions. Whatever columns have been used, you have to run an analyze command. And also, we have a parameter for analyze command, which is analyze threshold, which you can define as to how much amount of data has been added to the data. How much amount of data has been added to the table, so that you can skip analyze. Let's just say the set analyze threshold percentage to 20. The 20 will, if that percentage of rows that have been updated is less than 20, then it will skip the analyze command. Next maintenance activity we are going to see is vacuum. Basically, in Redshift, when you add a when you specify a sort key and disk key and install it, when you insert a table, the first time it will be perfectly sorted. But when you add another, you add a new data, the new data will be stored in a different space, and it won't be sorted. So the sort percentage of your table will be reducing, and hence. And also, when you delete a particular row from your table, the space will not be reclaimed. It will be marked as delete. So to reclaim the space and also to resort your table, we will use the vacuum. The vacuum is divided into vacuum full, vacuum delete, vacuum sort only, and vacuum reindex. Vacuum fill will reclaim the space that has been created by the delete command, and also the resort the tables, resort the rows that have been newly added. And vacuum delete only will only delete but not reclaim the space. Vacuum sort only, it will only sort but not only sort but not reclaim the space. And vacuum reindex, what it will do is for a interleaved sort key, you can analyze the sort key and do a full vacuum. Here, vacuum is considerably an input-output intensive operation. So what we can do is we can reduce the impact of the vacuum by the following things. One, we can use truncate instead of delete. And another, you can insert the data in a sorted order itself, and hence the vacuum will have less impact on the table. And also the vacuum can be scheduled on your ideal time of your cluster. You can let's just say weekend, your cluster utilization is very less, then you can perform your vacuum. The vacuum is also, we can specify the threshold for vacuum also. Let's just say more than this percentage is not unsorted, then only we can specify a vacuum to be happening, or more than this only, the sorted order has been disordered, then only vacuum has to be happening. We can specify that using a threshold command. Saravanan.
Yeah. Okay. Like so far, whatever we have seen is the features that exist in our current like production environment. Like some of these features that came into existence from say 2019. So AWS is something like they have introduced close to 200 features. Some of them are important. Like we are listing them a few here. That is like we are using them. We can say like we are using them. Okay. So these features are like say having an RA3, that is a third generation of compute, and then we are having something called Aqua, and we are having a new compression as Duga pointed out, like AZ64. We have materialized view that is new in like say Redshift. Spatial data support or federated queries or concurrent scaling. So we will be seeing like all this as a snippet, like okay. So we compress the data as said, like in order to have a like Redshift is a data warehouse environment, like it is going to be pretty much costly. So if we have to reduce space, like each column can be compressed on its own. So because it's not a row-based engine, it is a column-based engine, so that we can compress different columns at different lengths. We can compress to a different ratio when we compare it again with all other columns in my database. So like they introduced a proprietary compression called AZ64 back in 2019. So that saves up to say 60 to 70% of uncompressed column. So if you're having an uncompressed column, it can save up to 60 to 70%, thereby reducing overall. Like if you are able to use AZ64 effectively in your data warehouse, then you will be saving like so like you will be saving GBs of storage that you are going to be billed for. So like, and it also performs better when we like say when it is an uncompressed state, it is going to be performing 25% slower when we compare with AZ64. Like there are other compressions that we had seen earlier, like pretty much another comparison is like a Z standard, like which is having same footprint, like the compression ratio is going to be remaining same, but it is going to be 70% faster in terms of like encoding and decoding. The overall query execution will be faster. So this is something that has been introduced of late, and like we can make most out of AZ64 by assuming like by applying this compression to a numeric data type or a date or a timestamp. So this is AZ64 that has been recently introduced. And okay, consider Redshift is having some feature called Redshift Spectrum, okay, where we are going to have our say cold data that is being stored in our S3. Okay, so that is like historical information, like even more historical information that more than our current data warehouse can support or store. Okay, so we are going to have more historical information that being stored in an S3, and then we can access it in our Redshift by an external table. So that part is already there by something called a Redshift Spectrum. Now, like Redshift is also having a feature called federated queries. Like currently, this federated queries is supported for like so OLTP databases that is hosted on RDS, like Amazon RDS. It is a Postgres flavor again. So Redshift is a Postgres, and then currently it supports it supports to a Postgres version of say like a Postgres version of Aurora, or else like RDS Postgres SQL. Okay, so that is an OLTP setup. Say consider your application runs in that application. So you are performing your OLTP daily transactions happening into the database. That data can be queried by using a Redshift like your Redshift. So that is something called federated queries. Like federated query, the key thing here is like there is something called predicate pushdown, by which it means like you are not going to get entire records from your Postgres database and process in your Redshift. That's not going to happen. Whatever predicates or whatever conditions that we are going to apply will be pushed to the Postgres SQL engine, and then it will be filtered out. Only a subset of that can be, whatever subset that is required for us to process in our Redshift will be taken into our Redshift, and then we will be running this application. So this can be achieved by something called an external schema. Like currently, if we see, we are having an historical information in Redshift Spectrum S3 and a data lake, and then we are having part of information stored in Redshift data warehouse itself, and then we are also having current data that is being processed in today morning, like today whatever is being processed, that can also be like handled in by using something called federated query. This is there like from 2019 onwards. Okay, and then like MView is something like that has been long pending for implementation in Redshift point of view. That came into existence in 2019 as well. Like so MView, like MView is going to be like view is going to store a query, but MView is going to store a result of a query. So that is going to be behaving like a table. So it's going to have a computed result. You are having a complex join, or you are having a long running query. Say in your table, you are writing a custom SQL, a long running query that has to run every day and build a refresh out of it, like extract out of it. In such cases, we can have a materialized view in place, replace that complex custom SQL and replace this with an MView, where you can schedule your MView, you can refresh this MView. It can be done incrementally, or it can be done a full refresh. There are certain limitations related to when we can apply incremental refresh, because these are currently evolving stage. So these are not fully implemented. These are all currently in an evolving stage of Redshift. So these are the 3 features. The other features we will be seeing in subsequent slides. Okay. Okay. So there is something called like Aqua. So we are having automatic query accelerator. So this is something called automatic query accelerator. So this is like a hardware cache layer. So we are having a hardware cache layer that is made of FPGA, and it makes use of like AWS Nitro engines. Okay. So what it does is basically like it stores all the data in SSD. So even if you are using RA3, that is SSD, but it is going to have a caching layer for across all the compute nodes. You will have all the data present in this Aqua nodes like SSD. So whenever your compute node is submitting a query, it will hit your Aqua layer. The Aqua layer is going to do only 2 operations. One is going to be a filtering, one is going to be an aggregation. So if you are filtering, you are having a caching layer in between your compute nodes and your Aqua nodes, right? So whatever it is going to do is like it is going to filter and aggregate the results and pass on a subset of this result to your compute nodes. So instead of having entire records to be processed by your compute node, you will have a local Aqua node for across each compute node, and the data being cached in that Aqua node. So whenever you are running a query, first step will be hitting a subquery, and then it will hit the Aqua layer. And in the Aqua layer, you are going to filter out the unwanted records, or you are going to roll up the records by grouping them. So that aggregation will happen in Aqua layer. It will submit the results back to your compute nodes. That result is not going to be the entire data set. It is going to be a part of your data set. Thereby, your compute node will not have a necessity to run through all your data that you are storing in your compute node. So thereby increasing the performance up to 10x to your current setup or any cloud data warehouse setup. So that is specialty of Aqua. There is one catch to it, like Aqua is currently for only preview. And if you are already using an RA3 instance cluster, then you can subscribe for Aqua. Then AWS team will be able to set it up for preview. So this is in preview currently. Over to you, Durga. Yeah.
We'll see we have seen before that there are 3 types of nodes in Redshift cluster. One is dense compute, dense storage, and RA3. Dense compute and dense storage, the trade-off between dense compute and dense storage is RA3, in which it decouples the storage and the compute. Here we can design the node type which we are going to use based only on the compute power, because the storage has been completely separated from that of the node type, and hence everything the storage is being stored in the managed storage in S3. The cluster, can you click on here the data that is stored in S3, and also in RA3 nodes use something called as SSD cache, which stores all the hard data, as in the frequently accessed data has been stored in the SSD cache, and all the cold data has been stored in the S3. The data movement is being made fast using the high bandwidth networking, because of which you can make it faster. So, and also it also makes use of that when you resize a cluster in RA3 node, it will be faster because it doesn't have to redistribute the data from one node to the new node that has been created. Next slide, Saravanan. Another important feature that has been introduced recently is what is called as concurrency scaling, in which, let's just say in our use case, the utilization of the utilization of the cluster is mostly less than 60%, but only on cases of ETL load we will reach to 100%. On times of ETL load, the BA queries that have been run will be delayed, on which time only in the particular times of the week we will be needing more utilization power. If we add a new node for the cluster, we will have to pay for the new node throughout the week. Hence, we will use what is called as a concurrency scaling, which we enable a concurrency scaling whenever the utilization, we can specify the condition. We saw in the WLM specification, we can specify the number of concurrency and also the maximum concurrency percentage. Based on the concurrency percentage, usually it will use to store it in the queue. Instead of that, if we enable the auto scaling, it will trigger a transient cluster, which is of same configuration as that of the base cluster, and your queries that are waiting in the queue will be submitted to the transient cluster. Hence, the user won't see any delay, and the transient cluster will be charged only on second basis on which when the transient cluster has been active. And hence it is cost optimized. But there are some limitations to the transient clusters. The queries that can be run on transient clusters, only the select queries can be run on the transient cluster, and also external tables cannot be accessed from a transient cluster. And any table using an interleave sort key cannot be used on a transient cluster. But the plus point of the transient cluster is it provides a 30 credit hours on a monthly basis, and hence you can for a 30 hours that you have used a transient cluster, you don't have to pay for a month. Anything more than that, you will have to pay. And we can also specify certain parameters for that. You can limit the maximum number of transient cluster that can be found on your cluster, and also you can specify the usage limit for your cluster. As in, let's just say for a monthly basis, more than 30 hours, I don't want the transient, I don't want the auto concurrency to be disabled. I can specify it using the maximum usage utilization parameter. Based on it, whether you can disable the option or you can also send a SMS notification so that you will know that the maximum limit has been reached. Next slide. Another important addition to the Redshift is the Redshift Data API, which enables you to, which actually manages the cluster database connection. Let's just say you have to connect it from your core, you have to connect the ODBC or DDBC connection. Here, the Redshift Data API manages the connection on its own, so you don't have to manage any of the connection. So, when you can just hit the HTTPS API endpoint, based on this, the data will be closed. Data will be retrieved. The DB credentials, you don't have to mention it in your endpoint. Instead of it, you can show it in your secrets manager and use it along with your AWS SDK to fetch the data and store and display it in your code. Here, there are some limitations to the Redshift Data API. One is the query size. The maximum query statement size is 100 KB, and also the size of the query that has been query set result that has been returned is limited to 100 MB. And also the query that has been returned, it will be stored in your Redshift Data API for 24 hours for data retrieval. That's all. Any questions?
If you have any questions that we can discuss, one small correction would be like Aqua is advanced query accelerator. I mentioned it as wrongly as automatic. Like, is there any questions?
Yeah. So my question is like, can we use this Redshift as a proper backend for a typical application, or it's just meant for purely batch processing stuff?
Sriram, like I'm not able to hear you clearly.
Okay. So my question is it my voice is audible, right? Hello.
Yes, Sriram.
Yeah. Okay. So my question is, if can we use this Redshift as a proper backend for a typical, let's say, some 1,000 user web application? Is it okay, or we should think about other systems for this same scenario?
Like you cannot place a Redshift in those, like if you are planning for a transaction based application that you are going to have, it is going to perform like you are going to have a procedure and then you are going to execute that procedure for every insert or an update. That is not going to be optimal because of the like engine here is columnar structure, right? So it will be like very hard to locate a record and then perform an update or a delete or an insert. That's going to be hard here. Like that would require some normal instance of Postgres or an say Oracle or a SQL server will come into picture. That's where we have an index. Here we don't have any index to locate the record.
And in quick Google search, I'm able to see that still the updates are possible, right, in Redshift?
Yeah, we can do an update, but it's not going to be like a recommended for.
Yeah, okay. It's not recommended. Okay.
It's not recommended for an OLTP kind of a setup, like where we are having an application and that application is going to like execute a procedure and then load the data into my database. That's not like here. Here we can update, here you can do an insert, but it's not going to be like optimal way to handle it. So it can be done, but it's not like it's not day in day out we should be doing that.
Okay, got it. And one final question. In Oracle, we do have a kind of PSSQL procedure codes, right? Do we have any similar kind of scripting scenario, or just only SQL is the only option we can interact with the Redshift?
We have here stored procedure has been introduced in 2019 as well. So for Redshift, we can write a stored procedure, like we can have similar functionality. We can have a custom function by using Python. Also, we can define a user-defined function. There is no concept like a package here, but we do have a procedure that can be written. We have also functions, user-defined functions.
Okay, got it. Yeah, the user-defined function in the means say you want to do some kind of custom operation on each and every record of the table. Is that what you're saying? It's a custom function?
Correct. Like yeah, correct.
Okay, got it. Okay, yeah, nice presentation.
Thank you. Any other questions, or else we can wrap up the session? I guess like I'll stop sharing my screen and stop the recording.
Yep, thank you.